West versus East, the Flames versus the Oilers, Team Canada versus Team USA, Mothra versus Godzilla, P-Nail Bacon versus regular bacon, Ralph Klein versus that environmentalist he gave the finger that one time, me versus a polywire fencing reel. I get the damn things tangled up all the time. Organic agriculture versus climate change. There's lots of epic battles and rivalries out there, but one of the toughest adversaries humanity faces to this day is climate change, an opponent that's connected to so many things in life, like jobs, communities, the land, and the food we produce. I'm Derek Leahy, and this is Rural Routes to Climate Solutions. Last month, the scientific community released a devastating report that stated we had very precious time to do something about climate change. Now, U.S. scientist Dr. Tracy Misiewicz believes adopting organic agricultural practices is one of the best ways egg producers can combat climate change. Here's what Tracy has to say, what we have to expect from climate change in the future.
So things that we expect to happen, we expect more variable precipitation, we expect our carbon dioxide levels in the atmosphere to rise, we expect it to get warmer, we expect more severe droughts and heavy rain. And all of these are going to have effects on agricultural productivity in a number of ways. So higher CO2 and warmer weather, a lot of people might say, yeah, that sounds awesome. Our crops are going to love it. Yes, they will, but so will invasive weeds, so will pests, so will pathogens. So studies have shown us that with warming temperatures and increasing CO2, the establishment and persistence of weeds is likely to become a bigger challenge, and pests and pathogens ranges are likely to expand. So this is something that all farmers are going to have to deal with. Okay, so one of the biggest things that organic farmers do that increases our climate resiliency is focusing on soil health. And so when we talk about soil health, we're talking about nutrients, we're talking about the microbial community, and we're talking about soil organic matter, which is kind of the base of all that. And there's a lot of benefits to having soil organic matter in your soils. So soils that are higher in soil organic matter have reduced erosion. It protects those soils against compaction. It improves aeration, water filtration, and water holding capacity. And all of these characteristics are going to be really important when we're talking about drought or flooding.
Well, full disclosure here, Misiewicz is a big fan of organic agriculture. She's the Associate Director of Science Programs at the Organic Center, a nonprofit research organization based in Washington, D.C. She spoke in Red Deer at the Organic Alberta Conference last winter and presented some pretty compelling evidence that organic agriculture is a powerful tool that producers can use to not only build soil health, but help take on this monumental challenge humanity currently faces. So let's hear what Tracy has to say.
So agriculture is a major contributor to greenhouse gas emissions. Food systems contribute about 30% of our global man-made greenhouse gas emissions. And agricultural production contributes to about 80% of those total food system emissions. And these greenhouse gas emissions contribute directly to climate change. So when we think about climate change in agriculture, there's really two ways that we can be part of the solution and two ways that we can be part of the problem. The first is by either increasing or reducing our greenhouse gas emissions. And the second is by either releasing or sequestering carbon in our soils. So when we talk about agricultural greenhouse gas emissions, we typically classify them as either direct emissions or indirect emissions. So a direct emission is basically an emission that is emitted on the farm. So a prime example would be on-farm fossil fuel combustion to run tractors or irrigation pumps. It also includes methane release from livestock and livestock waste, and nitrous oxide release from the use of soil fertility management practices such as synthetic fertilizers, but also manure and legumes. Now, indirect emissions are emissions that are directly related to agricultural production, but they are not necessarily emitted on the farm. So these include things like carbon release due to land conversion. So for instance, if we take out a forest or a prairie to convert that to ag land, the carbon that was once sequestered in that plant material above and below the ground, so the leaves and the trunks and the roots, that will decompose, and that carbon dioxide, most of that carbon will make its way back into the atmosphere. And another really major indirect emission is fossil fuel use for the manufacture and transport of on-farm inputs. And in particular, the manufacture of synthetic ammonium nitrate fertilizer is a huge source of indirect emissions. So when we talk about this, what's happening is when we produce these synthetic fertilizers, we need a source of hydrogens for that chemical reaction that happens. And that chemical reaction, the hydrogen atoms usually come from natural gas or methane. So when we say that it is very energy intensive and creates a lot of greenhouse gases to create fertilizers, we're not talking about simply it uses a lot of energy to run that manufacturing plant. We actually need fossil fuels as an input, as an ingredient to create that final product, those synthetic fertilizers.
So first thing first, before we go on any further, I feel like it needs to be said, Tracy is like the funnest scientist you're ever going to meet. Her presentation was on the very last day of the Organic Alberta conference last year, and by that point, everybody's pretty tired. But still, Tracy was able just to wake us all up. She brought so much energy to her presentation. But my favorite memory of Tracy was actually just after the conference ended. We go outside, Tracy sees a patch of ice, and she just starts sliding on by. She's from San Jose, I believe, so she doesn't really have many chances to go sliding on ice. And it was just great to see her glide by with a big smile on her face. Anyway, I want to give you a quick breakdown of ag emissions in Alberta. Agriculture accounts for about 7% of greenhouse gases produced by the province, making it the fifth biggest emitter. It's nowhere near as high as emissions from oil and gas, transportation, or electricity, but this does mean agriculture produces more emissions than heating and cooling buildings in Alberta does. In Canada, the breakdown's fairly similar. Ag makes up about less than 10% of the total, and Alberta is about 1/3 of those emissions. The reason for that is, or at least it kind of makes sense, since Alberta, well, it has about 1/3 of all the ag land. Agriculture doesn't really have a carbon dioxide problem like most sectors do. Agriculture has more of a methane and a nitrous oxide problem. And if you remember, that's not a good thing. So in the first episode, I made this horrible attempt at humor talking about throwing underwear in people's faces. But if you remember from that episode, I mentioned that those two greenhouse gases, methane, nitrous oxide, are more powerful than CO2. A ton of carbon dioxide is not equal to a ton of nitrous oxide when we're talking about global warming potential. Emitting 1 ton of nitrous oxide is the equivalent of emitting 240 tons of carbon dioxide. Putting it another way, if 1 ton of carbon dioxide is a snowsuit, emitting 1 ton of nitrous oxide is like putting on 240 snowsuits. Methane is more than half of Alberta's ag emissions, and it's largely due to livestock, so livestock burping, farting, manure. Methane emissions seem to have stabilized in the last decade after really jumping up in the 90s and the early 2000s. Nitrous oxide, on the other hand, it's been steadily climbing in recent years, and this is largely due to synthetic fertilizers. Nitrous oxide makes up about 1/3 of total emissions. So there's work to be done if we're going to reach net zero emissions in agriculture and all other sectors. But unlike oil and gas or electricity or transportation, where you have technological solutions to deal with emissions, in agriculture we have a secret weapon. And the secret weapon is right underneath our nose. Well, okay, it's actually underneath our feet. Soil.
The Earth has lost 133 billion metric tons of carbon in our top 2 meters of soil globally, and that rate of loss has been increasing dramatically over the last 200 years. And that increase is largely due to the conversion of natural ecosystems to agricultural land, and also due to the intensification of our farming systems. But it doesn't have to be this way. So fortunately, soil is a renewable resource, and so we can put carbon back into the soil. So soil scientists have estimated that by restoration of degraded soils, we can sequester between 1 and 3 billion tons of carbon annually. That is a conservative estimate, and that would offset about 11 to 32% of our global greenhouse gas emissions. So we know that large-scale industrial agriculture is contributing to climate change, and it is depleting the carbon in our soils. And 2 of the most detrimental practices that are used is the overuse of synthetic fertilizers and the failure to incorporate organic matter back into the soil. Conversely, there's a growing body of research which really suggests that practices that are commonly used by organic farmers can contribute to climate change mitigation by increasing energy efficiency, by increasing carbon sequestration, and by reducing greenhouse gas emissions. So some of these practices include the use of buffers and hedgerows. So this conserves soil carbon, but it prevents it from physical loss due to erosion. The use of extended crop rotations, and the use of manure, compost, and legumes for soil fertility. And so this has two benefits. One, these practices are used in place of synthetic fertilizers, which, as I mentioned, are very energy inefficient. They use a lot of fossil fuels, but they also put organic matter back into the soil.
I never really thought of soil being a renewable resource before, but she has a point, but not in the same way wind or solar or hydro or electricity are renewable resources. But you can renew the soil in a sense by feeding it nutrients. We could build up soil carbon just as easily as we can deplete it. Now, as we said in our on-farm solar episode, so episode 2, if you're looking for ways to cut emissions and to reduce energy, you need to look at energy efficiency first. In that case, we were talking about energy efficiency in buildings. In this case, so farm energy efficiency, Tracy's not talking about switching over to LED light bulbs, which are important. Tracy is focusing on reducing the fossil fuel energy that goes into producing food. And just as a quick side note, last September, we held a farm energy efficiency workshop on the Cohen farm in Farintosh. Dakota Cohen is a really badass young farmer who's already making waves in the egg scene out here. Said something that really stuck in my mind. What he said was we need to differentiate between being efficient and being effective. It may be efficient to pop open a gate, let your cows into a new paddock, and leave them there for a week or so. Probably takes about, 20 minutes, hour to do that. But is it an effective way to manage the land? Maybe not, because you're not really utilizing cattle to build up soil health and fertility the same way you would in an intensive grazing system. Now, Dakota, he actually used the example of pesticides and fertilizers, so I can't quite remember how he said it, but what he said was pesticides and fertilizers, they're definitely efficient, they get the job done, but are they an effective way to manage cropland? Are we really taking advantage of the soil's ability to renew itself with a little bit of help from us? I'm not a grains guy. I've never worked cropland my entire life, so I don't really feel like I'm in a position to say anything here. Anyway, let's get back to Tracy and the carbon footprint of a loaf of bread.
Okay, so this study was looking at the environmental impact of a loaf of bread. And so what they did is they looked at every step in the process, and this is using primary data. So they scientists actually partnered with a bread company that knew the farm, and so they could quantify all of the practices, basically from getting the fields ready to planting the wheat all the way down to packing and dispatching and slicing that bread and getting it ready for the supermarket. And so what they found was that, so I'm going to be focusing on the second bar to the right. So that's global warming potential. And what they found was that over half of the environmental impact of bread, when we talk about global warming potential, was due to on-farm practices. And then they found that 43% of that total, of the entire impact, that's that big red bar there, that's due to the use of synthetic ammonium nitrate fertilizer. And so this, of course, has nothing to do with organic, because organic farmers don't use synthetic fertilizer, but that's one less environmental impact that we don't have. And by we, I mean you. Okay, and this is a study out of Canada. So this was basically, it was done in 2008, and they're modeling what would happen if we converted all of the corn, canola, soy, and wheat crops in Canada to organic production. And what they found was that if we did this, on average, crop production would consume 60% less energy. So the way that you read this graph is basically these bars are cumulative energy demand, and we see conventional corn, organic corn, so on and so forth, conventional, organic, conventional, organic. They also found that by converting, there would be 25% fewer global warming emissions and 80% fewer ozone depleting emissions, and this would lead to a much lower global warming potential. And these big changes that we're seeing here are directly related to fertility management. So again, all of this is tied to the lack of use of synthetic fertilizers in organic.
If you want to check out that Canadian study Tracy just mentioned, I didn't get a chance to read it myself or figure out which one she was talking about. I think I tracked it down. So the title, and pick up a pen and paper because it's got a really long name. The title is Scenario Modeling Potential Eco-Efficiency Gains from a Transition to Organic Agriculture, Life Cycle Perspectives on Canadian Canola, Corn, Soy, and Wheat Production. It was done by Dalhousie University in Halifax. I was able to find a copy of this at researchgate.net. So, organics clearly have an advantage over conventional agriculture when we're talking about carbon footprints here. Fossil fuels aren't really required to create manure, compost, green manures, basically all those things organic farmers use in place of synthetic fertilizer. But since conventional farmers spray to suppress weeds and pests, they don't really need to till, at least not in the same way quite a few organic producers need to. No-till, as we've understood for a while, is good for soil carbon. The less soil disturbance means more carbon can remain stored in the ground. Tracy mentioned we've already lost 133 billion metric tons of carbon from the soil, which is a number that you can't really get your head around. I can't even think of a good comparison. All I can say is one elephant is about 5 metric tons. That's a lot of elephants. So, does that mean conventional agriculture has the upper hand on organic agriculture when it comes to sequestering carbon dioxide from the atmosphere and then shoving it into the ground? Well, apparently not.
Okay, so now I'm going to transition and I'm going to show you some data that support these assertions. So this is research that came out of the University of Illinois, and they were comparing soil health in 9 long-term farming systems trials across the United States. And so each of these trials included plots that were organic. They utilized both manure and legumes for soil fertility. Another one was organic and utilized only legumes, and then the third was conventional. And all of these plots utilized tillage. So what they found was when they compared the organic manure and legume to the organic legume, there was no statistical difference in the amount of soil organic carbon in those plots. But when they compared the organic plots to the conventional plots, they found that there was a 14% increase in the soil organic carbon in the organic plots as compared to the conventional plots. So that, a lot of people are going to say, yeah, well, conventional farmers are utilizing no-till a lot, and organic farmers are really doing harm to the soil by utilizing tillage. So let's take a look at a study that compares organic till versus conventional no-till. So this is research out of the United States Department of Agriculture's Agricultural Research Service. So this is government research. This is a long-term study that took place. It started in 1996. It's still ongoing. And so what they did that a lot of studies don't normally do is they looked at the organic carbon to a depth of 1 meter. So most studies look at just at very shallow depths. If we look at that first graph, can everybody see which line is the organic line and which line is the conventional line? Okay, and so the y-axis, which is that vertical axis, that represents soil depth. So the top is 0, so you can think of that as the ground going down to 1 meter. And then the x-axis, which is at the top, which is that horizontal, that's the amount of soil organic carbon. So it increases as you move right. So you can see that it's the first about 8 centimeters, conventional no-till plots do have higher levels of soil organic carbon. But when we look from about 8 centimeters down to 40 centimeters, all of a sudden the organic plots have more soil organic carbon. And then from about 40 centimeters down to 1 meter, there's no statistical difference. And so if we go ahead and sum up all those measurements in that soil profile, what we see is what I'm showing you in the second graph there, which is that our organic tillage plots still have higher levels of soil organic carbon than those conventional no-till plots. And so they found that this was mostly the case because, again, in no-till, your plant residues are being deposited right on the surface, whereas in tillage, you're incorporating them deeper into the soil where they're more resilient to degradation. And so, I'm showing you this. I'm not saying that organic farmers shouldn't be trying to till with less frequency. We don't need to till as deep. Conservation tillage is good. It's something that we should be working towards. But even with tillage, organic is still outperforming compared to a lot of conventional.
As I said in episode 1, Cows and Climate Change, my tiny little brain has trouble understanding soil carbon sequestration. Every time I get it, or at least every time I think I get it, I read something new, then I go back to being confused. Like right now, what Tracy just said, I don't get how tilling in plant residue even deeper into the soil is even remotely better for soil carbon sequestration than no tillage. The part about carbon sequestration that always confuses me is how it relates to the carbon cycle. And we know that carbon, it's constantly cycling, being drawn down from the atmosphere by plants, then released back into the atmosphere when plants decompose. So if what goes down must go up again, how is that even close to being a climate solution? Well, Tracy provided us with a pretty darn good explanation on this one, and I think I finally get it now.
So soil organic carbon is important. It's important for carbon sequestration. And it can be broken down into two main pools. So a lot of times you'll just hear total soil organic carbon, but it's actually composed of two pools. One of those pools is called the labile pool. This is a pool that's broken down pretty readily by soil microbes, and so it's recycled back into the atmosphere. It's a really important pool of carbon when it comes to soil fertility, but it's not sequestering carbon. And then we have the second pool, which is the stable pool, and we call this humic substances. So humic substances are much more resistant to degradation by microbes, so they can be maintained in the soil for hundreds, sometimes thousands of years. So they're much more important when we're talking about long-term storage of carbon in the soils. And the two primary components of humic substances is humic acid and fulvic acid. But you don't have to remember that right now. I just want you to say soil organic carbon, two pools, labile pool, turning over rapidly, humic substances, stable, staying put, carbon sequestration.
All right, I'm going to try and take a crack at summarizing what Tracy just said right there. The labile carbon pool is comprised of plants, crop residue, and remnants of dead organisms, all decomposing rapidly and thus eventually releasing carbon dioxide into the atmosphere. Labile carbon is critical and directly linked to soil health and nutrient cycling. And then there's that stable carbon pool. It takes forever to decompose and decay. Humus is a good example of stable carbon. Stable carbon plays a critical role in soil density and the soil's ability to hold water nutrients. When we're talking about drawing CO2 out of the atmosphere, sequestering it in the ground, or carbon loss from soil, we're talking about that stable carbon pool.
So previously, most studies have not broken down soil organic carbon into these different components, and that's because until recently, the methods haven't existed to do it cheaply and efficiently. So most studies will use either total soil organic carbon, like the previous studies that I showed you, or soil organic matter, and then use that as a proxy for carbon sequestration. But because we know that total soil organic measurement includes that labile pool that's cycling rapidly, we can see how it's not necessarily the best measure of carbon sequestration. So the National Soil Project had developed these methods, and they had already done all the research on conventional farms. So they had collected soil samples from 728 farms across the United States, put together a database, and then we partnered with them to collect soil samples from organic farms. And we managed to bring in 659, I think, yes, samples to compare to what they had already done. And I just want to emphasize that our soil collection for both the conventional side and the organic side was blindly done. So we didn't reach out to farmers that we knew were using particular soil fertility management practices. We didn't reach out to farmers that we knew were using no-till or were tilling or anything like that. We reached out for organic. We reached out to every single USDA certified organic farmer in the United States. We told them we would give them the results of their soil tests, and we saw what came in. And what we found was pretty striking. So if you look at the bottom left graph, that's soil organic matter. This is a common measurement. So we found that our soils from organic farms had about 13% higher soil organic matter. This is what we expected, and it's in line with previous research. But what's really interesting is the top two graphs. So that's humic acid and fulvic acid. And if you recall, those are the two primary components of humic substances, that stable carbon sequestering pool. And we found that soils from organic farms had 150% more fulvic acid and 44% more humic acid. Then if you look to the bottom right, you see humification. Essentially what that is looking at the rate or the proportion of soil organic matter, a total that is converted into humic substances. So we have that total pool of soil organic matter. How much of that is going to go into that labile carbon pool versus how much is going to go into that sequestered pool? And we found that humification was 26% higher in organic soils versus conventional soils. So this study is pretty awesome because it has a huge sample size and across a broad geographic range. And we're still, in spite of all the variation in farming practices, both in conventional and organic, we're really able to discern the strong statistical effect of practice when it comes to carbon sequestration.
The main question on my mind after hearing about that study is, what is it about organic agriculture that makes the stable carbon pool so much higher than in conventional? Now, there was a study that was released last June by UC Berkeley showing planting cover crops, optimizing grazing, seeding legumes into pasture, and using biochar and compost. These all do help sequester carbon in soil. These practices, they're by no means exclusive to organic agriculture, but they are commonly used by organic farmers since they don't have that added helping hand in synthetic fertilizers. The study concluded if practices like the ones I just mentioned were adopted globally, farmers and ranchers around the world could help reduce the increase of the planet's average temperature by 1/4 degree Celsius, which I do realize that doesn't sound like a whole lot, but you got to look at it this way. Last October, the Intergovernmental Panel on Climate Change, the world's leading scientific body on climate change, said in a report we only have about a dozen years to stop the planet's average temperature from rising above that 1.5 degree limit. Right now, we're about 2/3 of the way there. Surpassing that limit, that means those doom and gloom scenarios we hear about in relation to climate change. So sea level rise, disappearing sea ice, Arctic sea ice, and increasing desertification. We are walking such a thin tightrope right now in relation to climate change that 1/4 degree can make a really big difference. Organic agriculture may also help us adapt to some of the challenges we face in our climate right now. In recent years, we've seen a lot more floods, droughts. Well, organic agriculture might be there to give us a helping hand.
So these results are from the Rodale long-term field trial system. And so what they're doing here is they're comparing plots that are under conventional production, organic production using legumes, and organic production using manure. And so what I'm showing you here are basically yields for maize during drought years. And so there's 6 drought years here. Let's look at the first 5 where the bars are pretty tall, they're looking normal. If we look at those drought years, we can see that the yields, the corn yields in the organic plots exceed the yields in the conventional plots in 4 out of those 5 drought years. And that's attributed to higher levels of soil organic matter and better soil health. Now you're probably wondering what's happening in year 99 there, what's going on? Well, that year was a crazy year in the Northeast. So in case you're unaware, these trials are taking place in Pennsylvania, which is the eastern coast of the United States. And the Northeast had a severe drought that year. And then that drought was followed immediately by torrential downpours due to hurricanes. So it's common, our hurricanes, they start in the Caribbean, they come up the East Coast, and they just dump rain on us. So this was severe drought followed by hard rain. So we can see that all of the plots really suffered here. But still, the organic plot that's treated with manure still has 38% higher yields than those conventional plots. So taken as a whole, this really shows us that soils that are high in organic matter and that are healthy are going to be more resilient to some of these extreme weather events. Okay, and then the other thing that we're worried about is pest and pathogen pressure. And so, again, organic farmers typically use integrative pest management techniques to control pests on their farms. And this is a study, these are results from a study. It was done in Germany. So they're comparing 15 conventional farms, cereal farms, to 15 organic cereal farms. And here what they're doing is they're looking at biodiversity. And here in particular, I'm showing you cereal aphids is what they're looking at. So you can see on the left, there's 2 bars. Those are the abundance, so the number of cereal aphids found in those conventional fields. And then to the right, there's 2 bars, and those are the number of cereal aphids found in those organic fields. And you're saying, why are there 2 bars for each of those? This study also compared the difference in abundance between the edge of the field and the center of the field. Just as a general rule, research finds that you're going to have higher biodiversity in the edge, along the edge of your fields than the center. But for the purpose of this talk, we can just ignore that and just sort of look at the combined results there. So what they found was that the abundance of cereal aphids was 5 times lower in the organic fields. And then they also looked at the natural predators of those aphids. So they looked at a variety of different predators, one of which was the beautiful lady beetle there. And they found that beneficial predator abundances were 3 times higher in the organic plots. And then when they looked at the predator to prey ratios, they found that they were 20 times higher in the organic fields. And what this shows is that when we support biodiversity and we have robust populations of beneficial predators, this just can provide us with an additional line of defense against emerging pest challenges that may be. So the sort of main take-home points here are that organic agriculture can positively impact climate change mitigation through carbon sequestration. It also tends to be more energy efficient, largely through the omission of fossil fuel-based fertilizers. And organic practices increase resiliency to climate change.
So really the key to all this is to keep your soil and your land as healthy as you can, which is pretty much a no-brainer if you're going to run a successful farm or ranch. And I know it really sounds like Tracy is beating up on conventional agriculture here. Sounds like a real conventional hater, eh? Well, not quite. I have a lot of respect for Tracy and what she said at the end of her presentation, despite working for an organization that promotes organic agriculture.
You know, I said all this, and I gave you all this data that's sort of comparing organic and conventional on average, but in reality, things are complicated, right? So those are the averages, and there's a lot of variation in this data. And in the end, you know, a good land manager is a good land manager. And what that means is that there are a lot of conventional farmers out there that are doing right. They are managing their land really well, and they are contributing to climate change mitigation. They are hosting beneficial biodiversity on their farms. And there are organic farmers out there that are just practicing input substitution, and they're not really doing a good job. So, you know, I'm showing you these averages. I think there's a lot of potential for organic agriculture, but, you know, in the end, it all comes down to individuals and what we're doing on our farms, what you are doing on your farms. So really, another thing that I want to highlight is that, you know, even if we're using best management practices, we need more research to develop those practices on regional, local scales, because what works in one place isn't necessarily going to work somewhere else. So we know from the research that the slope of your land matters, that the climate you're in matters, that your soil base matters. All of these things, your moisture content in your soil, all of these make a big difference. So when we're developing best practices, they need to be regional, they need to be local. And that's what I got for you. Thank you.
And that's our show for today. Thank you to Dr. Tracy Misiewicz of the Organic Center for your presentation last winter and for letting us use the presentation for this podcast episode. Also, I'd like to apologize to Tracy because I'm pretty sure I did not pronounce your last name correctly once this entire show. I am so very sorry about that. This podcast would not be possible without the financial support of the Alberta Real Estate Foundation. So thank you to you guys. We really appreciate all the help. Today's episode was recorded in a new studio. Right now I'm in the Media Lab in Calgary. Rural Routes to Climate Solutions is a central Alberta-based project empowering rural Albertans with climate solutions. We do the podcast, we run workshops, and we also do farm field days. Our next workshop will be in Stettler. We're going to be holding a workshop on how to Form your very own farmers cooperative. This will most likely take place on January 26th. Details, please go to the website www.rr2, that is a numeric 2, cs.ca. It's also where you can download other podcast episodes and just find out more about the Rural Roots project, or even send us an email or make a comment about what we're doing here. Rural Roots to Climate Solutions is backed up by an amazing advisory committee consisting of Brenda Barrett, Dana Penrice, who has left us and moved to Manitoba, but she's still helping us out, Mark Fox, and Kim Cornish. Happy farming wherever you are in Alberta. And remember, what's good for the farm is usually good for the climate.